Okay, ever stop and think about this? We take a simple element, silicon. It's literally the second most common thing in the Earth's crust, and we somehow turn it into the brain of every single smart device you own. It's wild. Today we're going to unpack that incredible journey, right from a humble rock to the absolute bedrock of modern electronics.
So the whole question really boils down to this, right? How do you take this, a material that's pretty much just fancy sand, and engineer it so precisely that it can run complex calculations or, just glow? The answer? Well, it's an absolute masterpiece of physics and engineering.
To even begin this whole transformation, we can't just scoop up any old silicon. Nope, we have to create a structure with incredible purity and perfect order. What we need is a perfect crystal.
But, here's the first major twist in the story. In its purest, most perfect form, silicon is actually a terrible conductor of electricity. It's basically an insulator. So why on earth would we start with something that doesn't even conduct?
So what you're seeing here is what's called intrinsic silicon, and the key thing to get is just how incredibly stable this stuff is. See, each silicon atom has 4 outer electrons, and it shares one with each of its 4 neighbors. It's kind of like all the atoms are holding hands in this perfect, rigid grid. They're locked in place, and that means their electrons are locked in place too. And if you have no free-moving electrons, you get no electrical current. Simple as that. Okay, to really get why they're so stuck, let's use an analogy. Think of an electron's energy as being like floors in a building, right? Down on the bottom, you've got the valence band. That's the crowded ground floor where all the electrons hang out. Then, way up top, you have the conduction band. Think of it like a totally empty superhighway. Now, for electricity to happen, an electron has to make the huge jump from that crowded bottom floor all the way out to that empty highway.
And this is the core of our problem. At absolute zero temperature, there's just no energy to make that happen. The valence band is totally full. The conduction band is totally empty, and there's this massive energy gap between them. So no electrons can make that jump. Period. Everything is completely locked down. Now, if we add a little bit of heat, a few, let's call them brave electrons, get just enough of a kick to leap up to the conduction band. And when an electron leaves, it creates this vacancy behind it, which we call a hole. And this hole can kind of move around too, acting like a positive charge. But this only creates a tiny trickle of current. I mean, not nearly enough to power a computer. So we're going to need a much better way.
And that better way? This is where the real genius comes in. It's a process that honestly sounds a little illicit, but it is the key to everything. It's called doping. And yeah, we are going to intentionally contaminate our perfect crystal.
So what is doping? It's the super-controlled introduction of a tiny, tiny amount of a specific impurity into that pure silicon crystal. This isn't about making things messy at all. It's about precision engineering, right down at the atomic level to completely change its electrical properties.
And there are basically 2 main flavors of doping you can do. For N-type, that's negative type, we add an element like phosphorus, which has 5 outer electrons. For P-type, or positive type, we use something like boron, which only has 3. So let's see what this actually does to our crystal.
Okay, look at the left. A phosphorus atom squeezes into the silicon grid. Now, 4 of its electrons form bonds just like silicon would, but that 5th electron, it's just left over. It's got nowhere to go, it's a free agent, just itching to move. Now on the right, the boron atom fits in, but it's short 1 electron. It only has 3 to share. This creates a really obvious vacancy, that hole we talked about, that's just begging to be filled by an electron from next door.
So how does this hack our energy building analogy? Well, N-type doping adds a new donor energy level, like a little stepping stool, right below the conduction band superhighway. That 5th electron hangs out there, and now it takes almost no energy for it to jump up and start conducting. And P-type, that adds an acceptor level just above the crowded ground floor, making it incredibly easy for an electron to hop up into that hole, which effectively lets the hole move around.
All right, so now we've got these 2 custom-built materials. One with a bunch of extra electrons and one with a bunch of extra holes. On their own, they're pretty useful, but when we stick them together, that's when the real magic happens. This combination creates one of the most fundamental components in all of electronics, the p-n junction.
Okay, check this out. The second these 2 materials touch, a little bit of chaos erupts right at the boundary. All those free electrons from the N side see the inviting holes on the P side, and they just rush across to fill them. This frantic recombination creates a very thin layer right at the junction. We call it the depletion region.
And in this region, there are no free charges left. It basically becomes an insulating barrier, and it stops any more electrons from crossing over.
But what if we apply a little voltage from the outside? So if we connect the positive end of a battery to the P side and the negative end to the N side, this is called forward bias, we start pushing the holes in the electrons towards the junction. This squishes that insulating barrier, the gate swings wide open, and bam, current flows right on through.
Okay, now let's flip the battery. This is called reverse bias. And, you guessed it, the exact opposite happens. The voltage now pulls the electrons and holes away from the junction. This makes that insulating region even wider than before. The gate doesn't just close, it slams shut. And almost zero current can get through. We've just built a one-way street for electricity. And the proof is right here in this graph. This shows you the current versus the voltage. On the right side, in forward bias, as soon as we apply just a little bit of voltage, the current just shoots up. But on the left side, in reverse bias, we can apply a whole lot of negative voltage and the current stays flat, right near zero. It's a perfect one-way electrical valve. So, okay, we've made an electrical gate. That's really cool. But how do we get from this one-way street all the way back to our original question, making light? Well, it turns out our little PN junction holds that secret too. And here it is. This is the big payoff. When we forward bias certain types of PN junctions, those electrons from the N side leap across that barrier, carrying a lot of extra energy. When they finally meet a hole on the P side and recombine, or fall into place, they have to get rid of that extra energy. And in special materials, like gallium arsenide, they release it not as heat, but as a photon, a particle of light. We've just made a light-emitting diode, an LED. And what's really amazing is that we get to choose the color, the size of that energy drop from the electron's high-energy state down to its resting state in the hole. That determines the energy of the photon, and that determines its color. It's like a bigger fall makes it different color light. So by using different semiconductor materials, gallium arsenide for red, gallium nitride for that bright blue, we can literally engineer light across the entire spectrum. But you have to understand this is so much bigger than just making pretty lights. That simple one-way gate, the PN junction, it's arguably one of the most important inventions in all of human history. See, that simple junction is a diode. But if you stack them together, say in a little NPN sandwich, you create a transistor. And a transistor is basically a tiny electrical switch with no moving parts. It lets a tiny current control a much larger one. And by shrinking these things down and cramming millions or now billions of them onto a single chip, well, that's how we get the integrated circuits that power our entire digital world.
So the next time you see a traffic light change, or use a calculator, or just glance at your phone, you're looking at the work of countless PN junctions. They are in our computers, our cars, they're even in solar cells, which basically just run this whole LED process in reverse. They absorb light to create a current. They are, quite simply, everywhere. So, really, the next time you pick up your phone, just remember this incredible journey. From a perfect but pretty useless crystal to a deliberately hacked, impure material that can control electricity and even create light. It just leaves you with this one big question. If we can do all this by engineering a rock to glow, what other seemingly impossible transformations are we just one clever hack away from engineering into the materials of tomorrow?